අපට මෙයාට එන්නේ N2O. This is the structure. So we have this. So another structure for this N double bond, O. Then this will be plus. Then this will be -2. So another structure. Then we can try some other structure like this. N double bonded to lone pair, and here only one minus. Right, then all together only 3 structures, no? So it is correct. Next one, the fourth. Among the second row element of the periodic table, fluorine has the largest negative value of electron gain energy. That's true. Why? Among all the elements, fluorine has the highest value is electron gain in is minus 349 kilojoules per mole. The second highest is for fluorine. That is minus 328 kilojoules per mole. Among all the elements, second highest is that. In other words, when we get that the element from lithium to fluorine, fluorine has the highest. Lithium to fluorine has the highest. So that's true. Next one, the boiling point of argon is higher than the chlorine. Boiling point of argon is higher than that of chlorine. How we can decide that? Equivalent argon and chlorine both are argon and Cl. Cl available as Cl2 in nature. So both are non-polar. The predominant intermolecular attraction is intermolecular interatomic attraction. Is London. Then London interaction depends on the molar mass, size, and the distance. When we compare the molar masses, argon 40, Cl2 71. And also Cl2 is bigger than, see, argon may be this much, but chlorine is a diatomic molecule, may be like this. And also here, the molar mass, size again, what we say. See, higher the size, bigger the size. So here we have to consider the contact area. Because of this, chlorine is a diatomic molecule. It is somewhat flattened than this. This is spherical, but this is flat. Therefore, this has a higher contact area. Therefore, definitely, chlorine will have the higher boiling point. Chlorine must have the higher boiling point. So this must be false. Understood?
Yes.
Okay. Next one. Neon has the highest first ionization energy among the noble gas. Helium, neon, and argon. Neon has the highest first ionization energy. No. We know that among all the elements in the periodic table, helium has the highest. Therefore, neon will never exceed that helium. So helium has the highest first ionization energy. So this is correct. 1, 2, 3, 4, 5. 5.5, 20 marks. Then part B. Draw the most acceptable Louis dot dash structure for the molecule. You modified that.
Hmm?
Did you modify that? The given structure.
Yes.
Wait. You have modified. How you know that something is the most acceptable structure or most stable structure? The skeleton of the molecule containing only NFS. This is okay. Yeah, this is the best. So the most acceptable may be this one. So you will get 5 marks for that. That's true. Oh, correct. Next one. U1. U1. Shape around the NS atom, and 2. The oxidation number of the atoms in the structure drawn into above. The one shape. One is the shape around this.
Yes.
We will first draw it in three-dimensional space like this. Fluorine, then nitrogen will have double bond, so it is bent here. Then sulfur, and sulfur has another 2 bond and 1 lone pair. So this will be fluorine and fluorine. So it will be around nitrogen. The shape is angular, correct? S, trigonal pyramidal. Yeah, that's correct. Nitrogen, the oxidation state. Oxidation state of nitrogen. How we can find it? It is like this. See, the electronegativity of fluorine is 4.0. Nitrogen 3.0. This is again 4.0 and 4.0. And this is 2.5. Therefore, what happens? This 2.5. Because of this 2 bond, nitrogen will get -2. Because of this bond, nitrogen will get +1. Because in this case, fluorine has the more electronegative. Among these, nitrogen is the more electronegative. Therefore, the algebraic sum is -1. So the oxidation state of nitrogen is -1. And the sulfur. All the atoms connected to sulfur or bonded to sulfur are more electronegative. Therefore, for each bond, sulfur will get +1, altogether +4. The oxidation state of sulfur is +4. and this is -1. Understood?
Yes.
Yeah. Therefore, you will get only 2 marks for that. Next one, a Louis that structure for the NO4 minus ion is given below. Draw 3 more Lewis dot dash structures. So personal structures for this ion. Lewis structure is given. You asked to draw some more. Let's see. Oxygen fulfill the octet. This will fulfill the octet. This fulfill the octet. But here, this oxygen does not fulfill the octet. Therefore, it is unstable and wrong. Right? Oxygen, nitrogen, fluorine must definitely fulfill the octet. In all the cases, there may be some few cases related to this nitrogen, like this NO2. In the case of NO2, or that see here NO2, it's okay. What is that? Yeah. Nitrogen has one which is just not the NO. If we get that NO, in the case of NO, nitrogen will not fulfill the octet. It may be the only exception, but in all the other cases, nitrogen will fulfill the octet, right? So, oxygen must definitely fulfill the octet, except in this O2 minus superoxide. In the case of superoxide, oxygen will have incomplete octet. Here minus, but here we have an unpaired electron. That's why it is not much stable. Because oxygen is now highly reactive. So remember that this is the only place where we can find oxygen which does not complete octet in its compound. Right? So, but here, as it does not fulfill the octet, that is wrong. In this case, nitrogen will not fulfill the octet, so it is wrong. In this case, this oxygen is wrong. Why? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oxygen will not exceed the octet because oxygen does not have empty orbitals to combine one more electron or no more electrons than 8. So oxygen will not exceed it. So that's wrong. That means all the structures are wrong. Let's try. Oxygen, oxygen, nitrogen, oxygen and oxygen. See, Puta, this. If you just interchange these two bonds, then you will get another structure. Very easily, you will get this structure. Minus, then double bond, lone pair, and here, two lone pairs, and here it will be minus like this, and here it is positive. Got it? And then another structure for this, you can try. You can give one electron to this, one electron to this, and this can be broken to other side. So oxygen double bond, oxygen single bond, nitrogen here, two single bonds. Means it will have like this, like this. And here plus charge. Here you will find a lone pair, and here like this. So it is Correct. Another correct structure. And some more structures you can try here. Oxygen, oxygen, nitrogen, oxygen, oxygen. Then you can put a double bond here. Then this is plus, this is minus, then like this. And here plus, here minus, here minus. Okay. I have drawn 3. Can you try one more?
Okay, sir.
Quickly, don't waste time. A structure is given. So you have to build the table. The number of Western pairs around the atom. C1 is this, it has 1, 2, 3 Western pairs. 3 sigma bonds and no lone pairs. Only the lone pairs and sigma bonds are the Western pairs. So it has 1, 2, 3 sigma bonds, it is correct. Then the electron pair geometry around the atom, if there is no lone pairs, the electron pair geometry and the shape of the molecule will be same. So it is trigonal plane and trigonal plane. The hybridization is 3 means sp2. 1s orbital and 2p orbitals will mix or hybrid to form this sp2 hybrid orbital or 3 orbitals. So it is correct. The entire column is correct. The second one, the N2, this one. Into 1, 2, 3, we have 3 Vesper pairs, 2 sigma bonds and 1 lone pair. Then the electron pair geometry is trigonal plane. The shape of the molecule is angular. Why? 2 bonds and 1 lone pair means it is angular. And the hybridization is again sp2. And in 3, this is the N3. So N3. N3 have 2 lone pairs and 2 bond pairs. Out of 4 Vesper pairs, electron pair geometry is tetrahedral, the shape is angular and sp3, correct. And info is 2 Vesper pairs because 1 sigma bond here and 1 sigma bond here means we have 2 sigma bonds around it and no lone pairs. So it is linear. The shape also linear because no lone pairs. And the finally SP. Hybridization is SP. So everything is correct. Therefore, you will get 16 marks for that. 1 mark for each. Then this is a very simple thing. Next part. Normally, if you have already identified the hybridizations here, then you can easily answer for this. And whenever hydrogen involved, you have to mention it as 1s, not just this. 1s. Without 1, that is wrong. You will not get marks. The C1, the hybridization of the C1 is sp2, so it is correct. Then C1 and N2, C1 again sp2 hybridized, same as that. Then N2 also sp2 hybridized. Therefore, this is correct. N2 and N3, N2 and N3, sp2 and sp3. So sp2, sp3. You have to just follow this. Then again N3 and N4. N4 was sp hybridized. See here, N4 was sp3 hybridized. Therefore, sp hybridized because it has triple bond, so it is sp hybridized. Then N4 again sp hybridized, and finally the N final N, that is just N. It has a triple bond, means it has two repulsive groups, one sigma bond and one lone pair, then it is sp hybridized. So it's P. Except the first one, all the others are correct. So you will get 9 marks for that. And here, look at this. All the elements except the side 9 second row means they have 2 p's to form 5 bonds. So all are 2p, 2p, 2p. Then you will get 6 for that. Next one is state the approximate bond angle around carbon, nitrogen, and carbon 1, nitrogen 2, 3, and 4. Carbon 1, nitrogen 2, 3, and 4. Carbon 1, 2, 3, and 4. So, here. Carbon 1 around the carbon 1, nearly it is 120 because trigonal plane nearly it is 120. So in such a case, Buddha, you will get marks for plus and 1. Plus or minus 1. That means 120 is the typical value for trigonal plane, but because of the presence of this high electron dense region, the repulsion may be little great. As they haven't mentioned or clearly specify which bond angle, this may be actually less than 120, maybe around 118, say, then this bond may be 121 because of this high repulsion between this high electron dense region and the bond electron. So anyway, you will get marks for 190 to 121. So 120. In such a case, you better if you don't write that 120 just because to be